Welcome to AP Stats Complete Review. So I won't be writing too much, but I will be talking a lot. Okay, so Chapter 2 talks about the 5 W's, which is who, what, when, where, why, and how. And what, you talk about the variables, which can either be categorical, which is, for example, the country, the state, the type, or time, which is quantitative, which always has a unit. And Chapter 3 is about summarizing categorical data, which you can do by doing bar charts, which has the frequency as the y-axis, relative frequency bar charts, segmented bar charts. There's contingency data tables, pie charts. And then Chapter 4, there is quantitative data, and use histograms, relative frequency histograms, dot plots, and when describing these, you want to use GSOCs or gaps, shape, outliers, center, and spread. So gaps pretty self-explanatory. Shape is a bimodal, multimodal, bimodal, unimodal, symmetrical or skewed, skewed right or skewed left, and then center. If it's skewed or with outliers, you'll use the median. If not, if it's symmetrical, then you can use mean or standard deviation for spread, and you can also do IQR and also range. So you usually use range. And then 5-number summary is how you'd make a box plot and use maximum, minimum, quartile 1, quartile 3, and the median. And there's also cumulative histograms. And now, on to Chapter 5 was about comparing distributions. So when you compare on the exam, you want to have context. You want to talk about the GSOCs if it's like a histogram or a bar chart. And you want to have like comparative terms such as the spread is greater than or less than or more, or comparative terms. And then Chapter 6 is about z-score and normal model. So z-scores have no units. They're the distance from the mean. And when it's normal, when a model's normal, the mean is 0 and the standard deviation is 1. And the farther, the more unusual. And when you shift, this center will add, so all positions will increase or decrease by the constant, but the spread will stay the same. You're just shifting it, so the spread doesn't change. But scaling both changes, both positions, which will be multiplied or divided, and the spread will also be multiplied or divided. And then normal models is a 68, 95, 99.7 rule. And so there's often a nearly normal condition. So is it roughly unimodal and roughly symmetrical? And you can also check if it's normal using normal probability plot. So if it's normal, that means the normal probability plot is straight. And also the difference between parameter and statistics. So parameter is population, so you can think P and P. And then statistics is summarizing, so S and S. And so, for example, parameters would be, for example, the new symbol, while stats would be like Y bar or X bar. Now into Chapter 7, we're talking about scattered plots and association. So when you want to describe scattered plots, you use FUDs, which is form, unusual features, direction, and strength. So form is a straight, curved. Talk about the pattern, unusual features, or the outliers. Direction is a positive, negative, or neither. And strength is a strong, weak, or moderate. And then the correlation coefficient is the strength of the linear association. So R is only accurate when it's linear. So R is the strength of the linear association, and then R squared R squared is like, for example, 77.3% of the variation in the in the y variable can be explained by the x variable or the linear regression model. So it's a measure of variation. And conditions for scatter plots, if you want it to be straight, is it straight enough? So you just see if it's straight enough. There is quantitative. It must be quantitative, not categorical. Are there any outliers, etc.? And the correlation coefficient is always between -1 to 1. -1 and 1 are both extremely strong, and 0 is very weak. 0 is no association at all. And don't get correlation and causation mixed up. You cannot say just because there's a correlation does not mean there's causation because of lurking variables. And chapter 8 was linear regression. So residuals is observed minus predicted, or y minus y hat. And the line of best fit is also the same thing as the least squares line. To find the slope, which is often b, you do the correlation coefficient times the standard deviation y over the standard deviation of x, and this formula is actually right over here to find slope. This is the common equation y hat equals a plus bx, where a is the intercept and b is the slope. This formula is just telling you how to find average, but you probably don't need that formula. This is how to find the standard deviation of, you see it's small s, so that means statistics, so it's a sample standard deviation. If it's population, then it'd just be divided by n, not divided by n minus 1. Back to this, the standard, so SE is the standard deviation of residuals, and the conditions are the same as the last chapters, and a residual scatter plot is where the x-axis is the x variable and the y variable is the residuals, which you can graph using your graphing calculator. So you could go to stat plot. I think I have as my third, and you can have y list be residual, and you'd have it as a plot. And so basically this tells you want to look if the scatter is random, not following any curve or any pattern. You want it like the scatter to be random. Chapter 9 is on regression outliers. So no extrapolation, that means don't predict like the future, for example, because you never know if it'll change. Outliers are when there's a large residual. So that means if it's high or low, while leverage is unusual x value, so is it far away from, so if all the points are here and then there's one point there, then you say it has large leverage. And an influential is when it changes, when the slope is changed because at that one point. So then you say the point is influential. Chapter 10 is about re-expression. So the goals of re-expression is to make the distribution more symmetric, make spreads more similar, make scatter plot more linear, or make spread more even. You can try things out. It can be logarithm, square root, reciprocals. Chapter 11 was about randomness and simulations. A component is, for example, opening a box, rolling a dice, selecting a student, etc. And simulations are randomly repeated trials that are supposed to model real-life situations, but it's often a cheaper way than having you go all out. And you want to describe the model, which is stating the component and how you will model, so like assigning the digits. For example, you'll use 2 digits or 1-digit numbers, and then you'll say something like 00 to 9. 00 to 09 is for the probability of saying the tennis racket breaks, and then 10 to 99 is the probability that doesn't break, for example. And you want to make sure that probability, that percent, matches the actual probability. And then you want to talk about, are repeats okay? Are they independent? Are the trials independent? And then you want to describe what steps will you take, what will you record. So you need to have a data table, and often the data table has a trial number. So it depends how many trials you want to do. But for example, if you have 5 trials, then you'd write 1, 2, 3, 4, 5. Next, you'd write the component, and then you'd write the response variable. And the response variable, you must write, state the response variable. And that's, for example, how many matches played before the racket breaks. So that's what you want to find. So you're often given random digits. And then over the random digits or in the table, you want to write if it's what it is. And then analyzing, you can summarize with GSOCs or means or the median. Oftentimes it's the mean. And so you say something like, based on my blank trials, I'd expect the racket to last an average of 5 to 6 matches before breaking, because I got an average of 4.4 or something like that. Chapter 12 was about sample surveys. So in samples, the fraction of the population that you sample doesn't matter. It's the sample size that is important. And bias versus variation. So bias is an accuracy issue, while variation is a consistency issue. And bias is a systematic failure, while variation is inherent error. So there will always be variation, but to reduce variation, you'll have a larger sample size. And to reduce bias, you want to make it random. Okay, and then sampling errors versus non-sampling error. Sampling errors, they're error in choosing the sample. For example, undercoverage is when parts of the population is not represented correctly. And bias sampling includes voluntary convenience, and non-sampling errors include like errors in the questions. For example, wording, they just answer wrong, they lie. Non-response is when the respondents can't respond. And then now onto the simple random sampling is when each element in the population has an equal chance of selection. And for example, systematic is example picking every 5 students on the list. A stratified example is or not example, but is when you slice into homogeneous groups and do a simple random sample within each strata. And this reduces variability and is more precise and gives better representation. So example stratified is, say you believe girls and boys get different grades, then you might divide the girls and the boys into strata and take simple random sample, say 50 girls and 50 boys from those 2 strata. Cluster is you take a simple random sample or census among the heterogeneous groups that resemble the population. And they are often, the benefit of that is it's often easier just to take the whole population, the whole cluster without having to divide them first. Parameter versus statistic, we already talked about that. Chapter 13 was about experiments and observational studies. So observational is observing, so there's no assigning or no manipulation of factors. There's retrospective or past and prospective observational studies, and you can't conclude cause and effect with observational studies. And in observational studies, you randomly select a sample. And in experiments, you do manipulate factors and levels to create treatments, and you randomly assign the sample to the treatments. And the factor is the explanatory variable, and the response variable is your result. And then when you have an experiment, you do not have the 10% condition. Well, observational studies, because you want to generalize to the population, you do have the 10% condition. And if the experiment is well conducted, you can conclude cause and effect. So observational, you can't conclude cause and effect. Experimental, you can. And the 4 principles of experimental design is control. So you want to make the conditions as similar as possible by controlling sources of variation other than the factors. So the factors will be different, but you want to keep everything else the same. Randomize. The subjects are assigned to treatments randomly. Replicate, you want to do this multiple times, and compare across the treatments. And blocking is like the optional part sometimes. And experiments, you don't always randomly draw from the population. You want to randomly assign. It's not necessarily always randomly selecting a sample. The control group is comparing without the treatment. Blinding is when, so there's single or double blind, and it's when single is when the subjects don't know, and double blind is when the subjects and the person analyzing doesn't know what treatment they're getting. And then confounding is when levels of one factor are associated with levels of another factor. So it's hard to see the differences because of the factors. And we already talked about lurking variable, how it is like a third variable that seems like it's causing causation when in reality it's not. And blocking versus matching. Blocking, each block is its own experiment. And when groups are similar, you block when groups are similar. And then matching is when each person is like an experiment. I mean, each person experiences the same thing, or two people who are extremely similar to each other experience the same thing. For example, if you're testing deodorant, one person might be smellier than the other and go through different experiences to make them smellier. But you can have one deodorant on one armpit and another brand on the other, and that would be matched. In blocking, for example, you could block by age, block by gender, little like stratified. And again, in blocking, within each block is like an experiment. Chapter 14, Chapter 14 is about randomness and probability. So law of large numbers is basically saying how it's long run, and same thing with the non-existent law of averages. Probability is long run, and when they're disjoint, that means there's no overlap. So when it's disjoint, you can say probability A or B equals probability A plus B. When it's independent, when the events are independent, you can say probability A and B equals probability A times probability of B. But disjoint events can't be independent. So if you have something that's disjoint, it's not independent. And I'll explain later. Sample space is a collection of all possible outcomes, and they always add to one. Chapter 15 more on probability. So probability of A or B, the general formula is probability A plus B minus probability A and B. So subtracting both of the overlapping sections. Probability A and B is probability of A times probability of B given A. And again, those two events do not need to be independent to use this formula. And probability of B given A is probability of A times probability of A and B over probability of A. To check if the events are independent of each other, you say probability of B given A equals probability of B. So you know the other event happens, but the probability stays the same, so they're independent. Or they're independent if probability A times B equals probability A times probability of B given A. And the reason why disjoint events can't be independent is because disjoint means events can't happen at the same time. So there's no overlap, but independent events must be able to happen at the same time. They just have no effect on each other. And chapter 15 also talked about tree diagrams. Chapter 16 was on random variables. So in the table, you'd often have the x value and the probability of that x value happening. And the expected is also the same thing as the mean, which is the center of a normal probability plot, normal model. And to find the center or the mean or the expected, you do the sum of the x value times the probability. So for example, say buying a small TV costs $60 and getting something, a small thing is $60 and the probability of getting that is 0.75, and a large is $200, but the probability is 0.25. So you'd first define what x is. So you can say x is the cost of repair, for example. And then, so the mean or the expected would be 60 times 0.75 plus 200 times 0.25. And the standard deviations is squared is equal to the variance. And standard deviation is the square root of 60 times, so the mean is $95. So it's 95 minus 60 squared times 0.75 plus 95 minus 200 squared plus 0.25. And then standard deviation, square root of that. And when you add a constant, it's like shifting. So the position will change. The position will be added, but so the mean will change, but the variance will stay the same. When you multiply by a constant, mean always acts as you expect it would, and variance would be c squared times variance x, or standard deviation times the constant. And when you add or subtract two random variables like x plus or minus y, it's always going to be addition, because your variance, you can only have more or the same amount of variation. You can't have less variation when you're adding to or subtracting to. And consecutive is when, for example, there's 10 of the same cars, like x1 plus x2 plus x3, then it seems like it's multiplying by a constant for the mean. For the standard deviation, though, you wouldn't square the constant. In chapter 17 were normal models, probability models like geometric and bimodal. Bernoulli trials, they have to have only two outcomes, a success and a failure. They must have probability of success is constant, and the trials must be independent. And if it's not independent, if it passes the 10% condition, you can continue. So geometric is the probability of success until, number x equals the number of trials until the first success. So x is the random variable. And binomial is the number of trials, the number of successes in the trials, in a certain number of trials. So for example, you have 12 trials, maybe 8 successes in 12 trials. And in binomial, you use n, choose x. And let's see, so if you look in your formula sheet, this is binomial. This is how you'd find the mean. Mean equals n times p. And the standard deviation for bimodal is square root npq. And over here, geometric, the mean is 1 over p, and standard deviation is q square root. I forgot to add square root q over p. Yeah, it's square root q over p. And then, sorry, I'm getting a little tired right now. Oh yes, and then this is how you can hand calculate it. So you use choosing here, geometric, use that. But let me show you how to do it on a calculator. So you'd go to second vars. You go for binomial. If you want an exact value, you go to PDF. If you want, like, if it's like a less than or greater than, you want to do CDF, but we're going to do PDF. So 12 trials, for example, the probability, say, is 0.6. Probability of success is P. The X value, so say we want to see the probability of getting 8 successes in 12 trials, that'd be 0.2, so not too bad. Now, geometric, PDF is an exact value. Say the probability is 0.5, X value is 4, it's 0.0625. Also, to hand calculate binomial, you can go to, so it'd be something like 0.6 times it'd be, you'd first go to math, prob, and CR, so back to example 12, 8 times 0.6 to the, say, 8, or I think, 0.6 to 8 times 0.4 to the 12 minus 8 is 4. And we get the same answer. Okay. Now we're on to chapter 18. It was about sampling distribution models, and proportion means is kind of an intro. So the central limiting theorem, CLT, for proportions is approximately normal for large n. So that's basic thing. As the sample size increases, it becomes more approximately normal. So now chapter 19, there are 1 proportion z intervals. And so this is proportions again, so it's a z. Z is proportion, T is means, chi is chi-test. Anyways, an example would be something like, we are 95% confident that between blank percent and blank percent of all tabby cats in this city are infected with this disease, for example. So that's interpreting the confidence interval. Now, interpreting the confidence level, if we repeated this process repeatedly with the same sample size, we would expect 95% of all samples to have a confidence interval that contains the true percent of all blank. So when interpreting the confidence level, the the confidence that contains the true percent. So not the sample percent, the true population percent. So the general formula for any confidence interval, as you can see here, is the statistics plus or minus the critical value times the standard error, which is the so critical value times margin error is the critical value times standard error is the margin of error, and the statistic in this case is p hat. So you're doing p hat plus or minus z star times p hat times q hat over n, and all that square rooted. And p hat is the estimated true population proportion. So p hat is the probability we observed, the proportion we observed in the sample. So p hat is sample, p is population. And how you do one proportion z interval on your graphing calculator. So you can do this with me. So stat test one proportion z interval, or z interval, or hold on, no. Let me see. Yep, one proportion z interval is A. So and that's how you do it. Next is, hold on a sec. So one proportion z interval. Oh yes, the condition. So conditions for z interval and z test are the same, one proportion. You always want to have the independence assumption because it's randomly selected sample and it's less than 10% of the population. And then you want to have success failure to be able to use to be able to say the sample size is large enough and to use a normal model. Next, chapter 20 was about one proportion z test. So hypothesis, hypothesis test, you want to talk about the hypothesis, the assumptions, the mechanics or the math section, and the conclusion. And so hypothesis example, this is example. The null hypothesis is the p equals 0.2, where p is the proportion of ingots that are cracked. And the alternate hypothesis is where p is not equal to 0.2. And because it's not equal, it's going to be two-sided. And then you have, again, the independence assumption because it's random, 10%, and success failure, and then so the sample size large enough. And then after assumptions, you want to write a statement that includes the test you're doing. So since the conditions are met, I'll do a one proportion z test. So that's the name of the test we're doing. And then you can get your calculator to also help you remember the math steps if you're forgetting. So stat test, one prop z test. And then you can do this, calculate, and that's what you get. And you want to do the mechanics if it's a free response. But this can help check your work and remind you of the math steps you might need to find. So for the math, you do standard deviation of p hat equals square root of p q over n. But this p q over n is not like the confidence interval where it's p hat q hat n. This is PQN, so it'd be 0.2, 0.8, 100. And jumping forward, two proportion test is also like that, PQ over N. And you can look at these formulas on the second page of your formula sheet. So we are on, for one population or one sample, it's PQ over N. Let me see something. Yep. Okay. Next you do. So, oh yeah, and then you find the z-score. So you do p hat minus p over standard deviation of p hat. So you actually don't use p hat that much until really finding the z-score. And then normal model. You have to shade in for the normal model, and then for the p-value, you can use your z-table or your calculator, and you say since the p-value of, for example, 0.01 is so low, I reject the null hypothesis. There is strong evidence that the cracking rate is not 20%. So it's different. It's not 20%. If the cracking rate was actually 20%, we expect to only see this 0.01 of the time. And then if the p-value is high, you fail to reject. And then you say there's not enough evidence to reject the null hypothesis, that p equals 0.2. Chapter 21 was about errors and power. So first, p-value is conditional probability. It's given the null hypothesis true, what is the probability of getting the observed proportion? So p-value is a conditional probability. And type 1 error is when the null hypothesis is true, but the researchers or whatever, or whoever is doing it mistakenly rejects it. So for example, the cracking rate is indeed 0.2, but they said that it is not 0.2. An example in a health way is, so when someone's healthy, it's always a null hypothesis. So say COVID-19 or no. So if no COVID-19, that's the null hypothesis. But a type 1 error would be the person doesn't have COVID-19. So they're healthy, but they said the test said that they do have COVID-19. The type 2 error is when the null hypothesis is false, but they fail to reject it, so they don't reject it. For example, COVID, so they are healthy. They are not healthy. They do have COVID-19, but they say they don't. They fail to detect that they do, that person has COVID-19. Okay, so that's type 1 and type 2 errors. Almost done. Alpha is the probability of a type 1 error when we reject null hypothesis. And if the p-value is lower than that, we reject the null hypothesis. That's called the significance level. And then there is beta, which is the probability of type 2 error. So power is 1 minus beta. And it's the probability that you correctly reject the null hypothesis. And power is conditional probability too. Okay. Effect size is the distance between PO and P. The confidence interval tells us the possible values of the parameter. And as alpha goes up, beta goes down, and power goes up, because when beta is a smaller number, 1 minus that will be a bigger number. Chapter 22, we're about two proportions. So the difference between two independent proportions is addition for standard deviation. And so first, the two proportions, the interval and a z-test, their conditions are the same. And it's the same as before, except we have one new condition, because now that there are two samples, we have to say the independent groups assumption. But first, say the independence assumption, because the randomly selected sample and less than 10% condition. And then you say the independent groups assumption, that the two groups are independent. So first you say the individuals, like results or whatever, are independent, and independent groups is those are independent of each other. Success failure is sample size is large enough. Same thing as last time. It's so you can use the normal model. And for the confidence interval, the calculation would be standard error p hat minus p hat 2 equals square root pq over n plus p2q2 over n. And the mean of the normal model would be p1 minus p2. An example is I am 95% confident that the proportion of blank is between 4.3 and 19.1 percentage points higher than the proportion of blank, or lower than blank. And pooling is a two-proportion z-test. So a two-proportion z-test is the same thing as pooling, and basically pooling it's when the mean, it's very similar to what you'd expect, except the main difference is you use the same p hat, so you pool it to find one p, and you use it the same for both of them. Next is so I'm getting a little tired right now. Next is the comparing two proportion z intervals. So you do p hat 1 minus p hat 2 plus or minus z star times the square root p1 q1 over n plus p2 q2 over n to n2. And then two proportion. Now on to t-test. So t-test is the mean and t-intervals. So one sample t-interval. First I forgot to talk about the calculator. So yes, you got a stat. So back to two proportion test. Two sample z interval. Two proportion z-test. Do that. And two proportion z interval, or two sample z interval, like that. Okay. Chapter 23. Okay, so the conditions, independent assumption, random 10%, nearly normal. So instead of success failure, you have the nearly normal, and you say it's roughly unimodal and symmetric. And one sample t-test for mean. And then so one sample t-interval. Example would be I am 90% confident that the interval from 29.5 miles per hour and 32.5 miles per hour contains the true mean speed of all cars on road blank. Degrees of freedom in one sample is n minus 1, and you do y bar plus or minus t star times the sample standard deviation over square root of n. And I am 90% confident. I missed that. So yeah, standard error is the s over square root n. And yeah, degree freedom. So when it's one sample, you can find the degrees of freedom. But when it's two samples, you have to use your calculator to find degree of freedom because it's a very complicated formula. So you say something for your conclusion for one sample t-test for means. Since a p-value of 0.136 is not low, I fail to reject the null hypothesis. There's not enough evidence that the average speed is too high. Or there isn't evidence that the average speed is too high. Comparing two means, so two sample t-interval and two sample t-test. The conditions are the same. Independent assumption, random 10% nearly normal condition, and the independent group assumption. So whenever you have two samples, you want to have the independence group assumption. So as you can see, the pattern for these assumptions are usually you have an independence assumption with a random and 10%. So if it's experiment, you will not have the 10% condition, and the random will be randomly assigned to treatments. But other than that, it's always independent assumption, randomly selected sample, and 10% condition, and then you'll have a nearly normal condition or a success failure condition. And that's basically, is the sample size large enough for success failure? And then you have independent groups if you have two groups. If you have one group, you do not have that condition. So comparing two sample t-intervals, I am 95% confident that people eating from refilling bowls will eat on average between 2.18 and 10.22 ounces more soup than those from an ordinary bowl. Two sample t-test, example conclusion, since the p-value is low, since a p-value of 0.03 is low, I reject the null hypothesis. There's strong evidence, ... You want to list out the sample size for t-tests. You want to list out the sample sizes for both groups, the mean for both groups, the standard deviation for both groups, and then so you can go back to your formula sheet. The formula sheet. And sorry, I just lost my train of thought. Oh yeah. So you can see these are for means. So what we're talking about now. This is how you find the standard deviation. This is how you find for two proportions. So for two proportions, the mean is just mean 1 minus mean 2. Degree, we talked about that. And then, so now on to chapter 25 is talking about parity interval. So parity intervals or parity tests act just like the one sample t interval, one sample t test. And you only look at the difference column. And the conditions are a little different because when they're paired, they are not independent of each other. They're naturally related to each other. So you'd have a paired data assumption. So you have an independent assumption, paired data assumption instead of independent group assumption, and the nearly normal condition. Since this is like a one sample t-test or t-interval, the degrees freedom is just n minus 1. You only look at the differences column. You don't look at the other two. So to find the t-score, you do the difference, the mean difference minus 0 over the standard error. And since the p-value is not low, I fail to reject the null hypothesis. There is an evidence to say the difference in speeds are significant, something like that. Last two chapters, chapter 26 is the goodness of fitness test, homogeneity, and chi-squared independence test. So these are for categorical variables. So since they're categorical variables, one of the conditions are counted data conditions. So the data are counts. The independence assumption, same thing, random or 10%. And then there's the expected self-frequency, which is similar to the success failure condition, in which it's saying the sample size is large enough, kind of. So it's saying at least 5 individuals in each cell, and I say sample size large enough. So again, the three conditions are independence of condition, counted data condition, and expected self-frequency at least 5. And chi-squared is the sum. Hold on, to write the formula right here. Chi-squared equals sum observed minus expected squared over expected. So really use your formula sheet during the test so you don't have to memorize everything. So that's chi-squared. So for goodness of fitness test on the graphing calculator, it's D. And then you type in observed, which is often L1, the expected, which is often L2, the degree of freedom, which is C minus 1, so number of columns minus 1, and you'll get a chi-squared and a p-value from doing that. So an example of goodness of fit test would be something like where you compare observed distribution of a single categorical variable from one group to an expected distribution based on a theory or model. For example, also chi tests are always skewed to the right, so it's always one-sided. And examples are deaths equal in all 4 seasons for doctors, or is blank the same? So you have one single population. And then homogeneity test is comparing the distribution of 2 or more groups for the same categorical variable. Instead of comparing distributions to an assumed model, we are comparing groups against each other. So we're comparing, for example, are the AP scores. You can compare the AP scores of these 4 different schools. That would be using a homogeneity test. And an example of a conclusion would be since a p-value of 0.004 is so low, I reject the null hypothesis. There's strong evidence that activities of students from the 4 colleges don't have the same distribution. Independence is whether the 2 categorical variables are independent. So the null hypothesis is tattoo status and hepatitis status are independent. So you want to see if there's association, for example, and the calculations are very similar, are practically the same in independence and homogeneity tests, where you have a matrix with the observed and the expected the graphing calculator will actually find for you. Let me see. Next is last chapter 27 is on regressions. So in the table, you'll often have an intercept, and then below that you'd have like the explanatory variable. And you want to look at the explanatory variable one. So if you go across the explanatory variable, you'll get explanatory variable, the slope, and the standard error. And you want to look at all of those. And the regression line assumes the mean of the distributions fall along the line. And the residual error is y minus y hat. The mean is the intercept minus the slope times x. For example, does a person's cholesterol level change with age? You could do null hypothesis is the beta 1 equals 0. The alternate hypothesis is beta is not equal to 0. So there is no change of cholesterol level. So when the slope is 0, there is no association. There is no change. But there is a change when beta 1 is not 0. I mean, there is an association. There is a change. So the conditions are independent assumption of y variables or observations are independent because it's a random sample, and the residual plot has no patterns. The straight enough condition, the scatter plot is nearly linear, and the residual plot has random scatter. There's a plot thicken condition and nearly normal residuals. histogram, residuals, normal probability plot for residuals is linear, and then you'll say that since the conditions are met, I'll do a regression slope t-test. And remember, for the regression slope t-test, you're looking, is the slope 0 or not 0? And you can do a confidence interval for the slope, where it's the b1 plus or minus the t star. Degree of freedom is n minus 2. So degree of freedom for one samples are always n minus 1, but for regressions, it's n minus 2. Example would be, I am 95% confident that the cholesterol levels have been increasing on average between 0.03 and 0.12 units more each year with age. And then you can also do a linear regression t-test, which is F on your graphing calculator. You type in L1, the X list, and L2, the Y list. Frequency is 1, and they calculate the equation, the t, the p-value, the degrees of freedom. And yeah, so that is a review. I hope it was helpful, and thanks for watching.